So last time we had talked about, so till now we have talked about so we have talked about amplitude modulation. One, two, my laptop is, yeah, we have talked about three SSB. For some reason my laptop screen is slightly misbehaving today. So we'll possibly yes. And three, we have talked about single sideband modulated signals, and we have talked about demodulating these signals as well. So now the question is that, okay, so the problem is that my laptop has suddenly become laggy. So let's see if it works properly
Sir,
now. So
restarting would be helpful.
restarting would also cost 10 minutes.
Okay.
Even I know that restarting is helpful, and I've seen multiple joke videos of online classes where they tell people that, oh, sir, your laptop is not, we cannot see your screen, press Alt F4 and everything will work well.
No, sir. I
Yeah,
actually
I know that, I know that. So,
my
but
laptop is also touch screen, so sometimes
yeah,
this happens.
yeah, so this happens. I don't know why it's happening now. And I also know that restarting helps. But right now, so anyway, see this thing. I don't know why it's slow. So anyway, we have this message signal empty. Fine. Now let us consider the special case. Okay, this is embarrassing. Let me close a few applications and then see if things work. Maybe something useless is, oh, 100% CPU usage, 100% disk usage. No doubt this is troubling. Let's kill the programs with the highest disk usage. That should help. Systems. No. System has the highest disk usage. So I cannot even kill the program with the highest disk usage. Yeah, let's try to continue and see what happens. Now, let us consider the special case This is too irritating. Okay, so what I'll do is I'll read out using the Word document. Yes. So you can see the screen now, right? So
Yes, sir.
so we consider this special case, quadrature carrier multiplexing. We have, meanwhile, I'll restart the laptop. So, yes. So we consider this special case, quadrature carrier multiplexing. Let us now have the signal. We have discussed coaster receiver, and so let us now consider the signal ST equals MIT cos 2 pi FCT plus MQT sin 2 pi FCT. So where MI and MQ are both real valued signals, band limited to W. And now let's say that uh, letting Si prime t equals St cos 2 pi FCT and Sq prime t equals St sin 2 pi FCT, we will get this beast Si prime t equals MIT 1 plus cos 4 pi FCT plus MQT sin 2 pi FCT sin 4 pi FCT, and passing these through a low pass filter, I get this. Fine. So I can actually transmit two signals, each with bandwidth W over NAM signal, and we are actually, when we do that MT cos 2 pi FCT, we are actually wasting bandwidth. So this is one motivation for using single sideband, that we can transmit two signals parallelly over here. You get the point? I'll write this down as soon as the laptop restarts. So
So, do the subscripts I and Q have a significance?
yeah, in phase and quadrature. So the signal multiplying the real part or the cos 2 pi FCT, since we is called the in phase component, and the signal multiplying the sin 2 pi FCT part is called the quadrature component, since they are in phase quadrature or they have a pi by 2 phase difference. That's why. So laptop is still restarting. So I can actually, you can also see these as that. So since we are wasting resources, this lady is angry because we'll be. So anyway, we are. So alternatively, say that. Say if M if MT equals MIT plus JMQT. So this M tilde T is a complex valued signal, and consequently ST equals m t e to the power j. Sorry, this has to be minus. The real part of this. So this st is basically the real part of this mt e to the power j 2 pi fct. Now the question is that can I think of having single sideband modulation for m tilde t, or for the complex baseband signal mt m tilde t? Can I have single sideband modulation? Anyone? Because Windows has started updating on that thing. So yeah, can I have single sideband modulation for MT, M tilde T? Try guessing.
Sir,
Yeah.
what is M exactly out here? Because I didn't get it. I have.
So MIT and MQT are two real valued band limited signals, band limited W.
Okay.
And I define M tilde
Okay.
T like
Are,
this.
are these two different signals?
Yes, these are two different
Okay.
signals.
And we are what modulation are we using?
We are simply transmitting this ST equals real part of MT e to power j 2 pi fct, that equals this ST.
Okay.
Okay. Now my question is, can I use for this M tilde T, for this kind of a signal, can I use single sideband modulation? Why or why not?
Since this is a complex signal,
Yes.
we can't use single side modulation, right?
Elaborate slightly more.
Because it is not symmetric about the.
Yes. It is not symmetric about the y-axis.
Yeah.
So we cannot use single sideband modulation. So Windows is still updating, and actually with this you can see that so this technique of multiplexing two signals onto a single double sideband modulated signal is known as quadrature carrier multiplexing. Since you are over the same carrier, you are transmitting two signals. So you are essentially multiplexing two signals that can be demultiplexed appropriately using the sine 2 pi fct carrier, or the which is the cos 2 pi fct carrier, which is the in phase carrier, or the quadrature carrier, which is sine 2 pi fct. The only thing that you require over here is a precise phase synchronization between the transmitter and the receiver, so that you don't get errors like the ones you got earlier, or the ones that prompted us to use Costa's receiver. Because here again, the Costa's receiver won't work. And using this as well, you can see that if and and MQT equals minus M hat T, then we get single sideband. Then we get single sideband modulation. This is okay.
So aren't we trying to send two baseband signals?
Yes, we can try to send two baseband signals. That is one way, one use of these quadrature carriers. Another use is that if we are trying to send just one baseband signal, we can try this as well.
Okay.
Okay, so see, if you have two baseband signals, you can multiplex them to get this. Alternatively, if you want to send just one baseband signal, you can replace MQT by the Hilbert transform of the first signal, and you'll be able to save bandwidth. Using single sideband modulation techniques. So that is the key takeaway, and that's what we call quadrature amplitude multiplexing. So laptop has started. Let me launch Teams and start OneNote. So this was all about angle modulation, amplitude modulation that I wanted to discuss. The next topic. So let's give you some practice questions. So yes. Again, Simon Higgins textbook. Chapter 3. Three point 1 to 3.7. Nine, 10, 3.9 to 12, then 14 to 16. I've actually given out as 14 to 21. I've given out as the video exercises. So these involve slightly more thinking, and they are not directly available in the solution manual. So these I have given out to people as the video exercises. You can look at these and try to solve these beforehand. Actually, you can discuss them, so it makes life easier for people who are making videos.
So we can randomly choose one of that question, or
No,
you'll be.
so here I'll show you, since the laptop is troubling. So I'll show you what we'll do. So video, yes. So here are 12 questions. These I can show you because anyway you will be, this is not a test and you will be getting one of these questions. So let's see, 15, 19, 21, 24, 14, 14, 15, 19, 21, 24. You have to make a 3 to 5 minute video explaining whatever I've asked in the question. So what I'll do is I'll basically be sending you one of these questions via email. And your video can include video can include, you can use a PowerPoint presentation with voice narration. So you can, you know that you can, in PowerPoint, if I go here, so actually what you can do is you can open a new presentation, and here say I want to insert the discussion. So insert screen recording. So it will show me something like this. I select the area that I want to record, and I click on record, and PowerPoint records my screen. So you can either you can use PowerPoint to record the video, you can use your hands and you ask someone to hold the phone while you record the video. You can use a tripod stand. You can record narration on PowerPoint slides, but you have to record a video, and so you'll be given 1 week for that. So that's okay. Cancel this. So any questions regarding this? Because before I start angle modulation, it's good that we discuss. So yes, any doubts with amplitude modulation? Chat. Yes, so I looked at the chat just now. Yes, and showing. So the laptop has restarted. So yes, if you guys have any doubts, you can ask right now. The laptop is still acting.
Sir, regarding the recording, can we use the Teams recording?
You can use anything. That PowerPoint screen recording feature, since many people don't know about it, that's why I told you about it.
Okay.
You can record any way you like. I am happy with that. So you can actually, if you are not comfortable with videos, you can actually send. You can use some still pictures with a. So you can write something on the paper, click still pictures, and add your voice narration to that. And I'll also be happy with that. So it's not that I want a high quality video. I simply want a good explanation, whichever way it's given. So I think that we should be able to restart our discussion. Yes. So we can. So we have discussed this, and so yes, now it's fine. So being done with amplitude modulation, now let's start the second chapter. Angle modulation. So we had seen that that carrier signal looks like CT equals AC cos theta CT. Right. So we get amplitude modulation when we change AC with respect to the message that want to transmit. We get amplitude modulation when we change AC, when we change AC with respect to the message that we want to transmit. If we change, so this theta CT is the angle, angle of the carrier change get angle modulation. So we get angle modulation, and we only focus on cases where this theta CT is a non-decreasing function of time. So we'll only focus on the cases where theta CT, the angle, is a non-decreasing function of time. So we work under this constraint. Now, given this constraint, how do we change the angle of the carrier signal in proportion to the modulating signal so that we get our message across? Any guesses? Okay, no guesses. So actually, if you think clearly about it, there are actually, once we discuss the examples, there actually are infinite ways of achieving angle modulation. You have seen that we have discussed 3 ways of achieving amplitude modulation, right? So likewise, there are infinite ways of achieving angle modulation, but we'll focus just two, namely frequency modulation to phase modulation. So we'll define both of these in today's class. But before we discuss this, we'll have to revisit the notion of frequency. So in general, if the angle of a signal is non-decreasing time, we say that a complete oscillation has occurred. Yeah, Shubhashish, you want to say something? Angle has increased by 2 pi. Right, this is how we define an oscillation. So in general, for frequency Fi and a time interval delta can write theta c t plus delta equals theta c t plus 2 pi, right? Based on this,
Sir, are the two deltas different?
oh sorry, thank you. That was what should I say? Involuntary mistake. So based on this, I can write Fi equals theta c. Sorry, wrong delta again. Right. This is how I can define the frequency of a signal. Now, if so, this is the case when the angle of the carrier signal is changing linear when the angle of the carrier signal is changing linearly with time. So now let's say that theta ct changing non-linearly with time and we want to fit a piecewise linear model, then if we want to fit a piecewise linear model, then the frequency at each instant of time will be different. Let us call this instantaneous. Let us call this instantaneous frequency. And based on this, the instantaneous frequency at time t, or the average frequency time t at time t for an interval delta is fi t t plus delta, wrong delta, theta c t plus delta minus theta c t divided by 2 pi delta, and the instantaneous frequency is, yeah, so you can tell where are we going just by looking at it, can't you? So where are we going in this?
Derivative.
Yes, derivative. So, and the instantaneous frequency is fit. Sorry, this wasn't written properly. Fit equals limit delta tends to 0 theta c t plus delta minus theta c t divided by 2 pi delta equals 1 upon 2 pi d theta c t divided by dt. And based on this, if we want to frequency modulate signal this is called the hertz per volt. Fine. So if I change the instantaneous frequency of a signal like this, I can achieve what is known as frequency modulation. And based on the definition, theta it equals integral minus infinity to 0 or minus infinity to t 2 pi fi t dt. And assuming the signal to start at time 0, or this signal is causal. There is no such thing as a causal signal actually, but still the signal starts at time 0. There's only a causal system, not a causal signal. Theta it equals 2 pi fct plus 2 pi kf integral 0 to t m tau d tau. And the modulated signal becomes AC cos 2 pi fct plus 2 pi kf 0 to t m tau d tau. Alternatively, fine, this is how a frequency modulated signal is. And alternatively, we can view the angle of the carrier signal as theta ct equals 2 pi fct. Oh, sorry, plus phi it, where phi I is the initial phase. So if we keep the frequency constant and try to modify the initial phase as a function of time, so try to modify the initial phase as a function of time, we achieve phase modulation. Fine, we achieve phase modulation, and in this case, defining phase sensitivity as Kp, get theta ct equals 2 pi fct plus Kp into mt.
Sir,
Yeah, Aditya.
the reason we are modulating is because we want to send the message signal in form of either the amplitude, the frequency, or the phase. Is that right?
We want to send a message signal. That's why we are modulating. So amplitude, we have seen how we can play with the amplitude of a carrier signal and send the message. We are trying to hide or embed the message in the angle of the signal that we are sending.
So, but if we are embedding it in the phase, then are we not limiting how much we can embed?
No, no, we are not.
Okay.
So actually what you see is that if I look at, so for an FM signal, theta ct equals 2 pi fct plus 2 pi kf integral 0 to t mt dt. Fine. So
FM is frequency modulation?
yes, FM is frequency modulation. So the FM that you have in your cars and your cell phones, that is frequency modulation. That uses exactly this technology.
Okay, sir.
Okay. So
And so one last question. So
yes,
we are embedding the amplitude of the message signal in the phase right now,
yes, in the phase or the frequency.
but we are embedding the amplitude of the message signal,
Yes,
right?
we are embedding the amplitude, or we are actually embedding the waveform of the message signal,
Okay. Come the
to be
complete
precise.
signal itself.
Yes. So we are embedding the complete MT.
Okay.
So if you now look at equations A and B, you can see that if frequency, or if I phase modulate a signal with integral 0 to t, sorry, this should be m tau, not mt, because t is the outer variable. So m tau d tau, t m tau d tau. If I phase modulate a signal with 0 to t m tau d tau, then I achieve frequency modulation. Similarly, if I frequency modulate a signal with dmt by dt, then achieve phase modulation. Fine. So phase modulation and frequency modulation are actually interchangeable. So now let us look at some properties of phase modulation and of angle modulation in general. So some properties of angle.
Sir, if they are interchangeable, why are they called two different things?
They are not exactly interchangeable. We'll eventually see that there's a form of FM that can be interchanged with amplitude modulation. That's one
Oh,
thing.
okay.
Two, both of these, we are studying both of these under the general umbrella of angle modulation.
Okay, sir.
Okay, so we are generally discussing angle modulation, but there are actually infinite ways of generating an angle modulated signal.
And we are just discussing two.
We are just discussing two, which also reduce to the same thing.
Oh, okay.
And out of these, frequency modulation is more popular.
Yes, sir.
So this, and we now look at some properties of angle modulation. One, these are constant amplitude signals and the average transmitted power also remains unchanged. This is one. Two, the modulation process is nonlinear. That is, if mt equals m1t plus the am1t plus b m2t, s1t equals ac cos 2 pi fct plus 2 pi kf 0 to t m1u du or m1 tau d tau, whichever way you want to write it, s2 t equals ac cos, so I can get rid of this actually, ac cos 2 pi fct plus 2 pi kf 0 to t m2 tau d tau. Then st equals ac cos 2 pi fct plus 2 pi kf 0 to t m tau d tau is not equal to s1t plus s2t. This is fairly obvious, right? So these are angle modulation is a nonlinear process. Three, these signals are, it's hard to, what should I say? It is hard to have an intuitive form of these signals. So amplitude modulation, you could see that you have the envelope varying directly with the true signal, but in case of frequency modulation or phase modulation, you cannot straightforward see anything. To illustrate this, consider this picture. So paste. So I'll So yes. This is the case where we modulate a sinusoidal carrier having a frequency 10 Hz with a sinusoidal signal having a frequency 1 Hz using kf is equal to 0.5. We do see that the frequency of the frequency of the carrier change with a possible change in the amplitude of the signal, but we cannot intuitively draw this picture as easily as we could have drawn an AM signal generated using the same process. That is one. Two, this is for a pure sinusoid where the compressions and rarefaction. So it also, you can see that the amplitude of the signal actually causes compressions and rarefactions in the frequency. And three, this is for a pure sinusoid where it's still simple. As we go towards more complicated signals, life will become harder. So you cannot actually have a intuitive waveform for an FM signal. That's why from this point on, we'll focus more on mathematics rather than waveforms and circuits. Or we'll focus more on mathematics. We'll still have to deal with some circuits. And this also leads to a better signal to noise ratio. But since we have not discussed noise yet, we'll leave this property. And there's one more property related to the zero crossings that we'll discuss in the next class, because that will take some time. So any questions? Yeah, Kirti. Kirti, you want to ask something?
Sir.
Yeah. Fire away.
Sir, am I audible?
Yes, someone is audible, but I cannot see your name. Yeah, Shubhashish, now you're visible as well as audible. Tell me.
Someone was kicking me out constantly. Okay. The Microsoft Word file that you have changed, will you be uploading it again?
So that's automatically uploaded.
Okay.
So that is like a live version.
Okay.
Okay. So that's all. Yeah. So stop playing pranks on each other.
So I've been kicked about 8 times.
No, that's what I'm. Yeah. Okay. So actually, that would happen. So once the lecture is over or something, so there are talks. So when the lecture is over and you are okay, everyone wants to go, and then someone starts asking something, and everyone is like, "Murder this guy." Maybe that's why. So it's natural, but you guys shouldn't prank each other. That's not good as long as the class is going on. Yeah. So I cannot lock anyone. Maybe maybe I can try something with the settings so that only I can kick out people from the meetings.
You can make everyone an attendee, sir.
Yeah,
Yes,
that I'll do. That I'll do. Yeah, so I'll do that from the next time. Sorry for today, Shubhashish. I didn't know that. Well, I could have done that, but I didn't think of that. Yeah, I'll take care of that.
So I almost felt like starting myself.
Yeah, sorry. I'm sorry about that. I didn't know this would happen. From next time on, I'll make everyone else an attendee. Yeah, okay. Bye then. Have a nice weekend, all of you. Short
Same
weekend.
to you, sir.
Don't step out. Bye.